See, I was trying to prove this proposition. X is a quasi-affine and Y is affine. Then morphism between X and Y. So of course in quasi-affine category. So this is same as same means one-to-one bijection. Morphism between OY and OX as K algebra. This is what I was trying to prove last time. So of course, if you have a morphism between this is okay, right? So this already I saw that if you have two map phi and psi, if they are in morphism xy quasi-affine such that phi upper star and psi upper star both are mapped from OY to OX. If phi upper star equal to psi upper star, this will imply that phi equal to psi, right? This we have seen. So, but now the surjective part that so this is the injective part, and the surjective part is that if you take something in map from OY to OX, you want to construct a map of A from X to Y, or K algebra map, K algebra homomorphism. And you want to produce some phi. So Y is a affine variety. So Y is in some AM. And suppose Y is given by some ideal, say F1, F2. Okay, let's write V of P, where P is a prime ideal. Now you want to define a map from X to Y. So first you define set theoretically that so to define a map from phi from X to Y, you have to define a algebraic map from phi X to N, and then you should show that the image is lying in Y. So how do you do it? So you have this phi I. Phi I is nothing but xi composition phi I. Xi is the projection to the ith coordinate, and consider phi I. So no, sorry, what I'm saying, phi I want to produce a phi. Okay, you have to use this. This F is a map given. So OI is what? OI is nothing but KY, AY, and this is nothing but KY1, Y2, YM modulo some prime ideal. So now from OY to OX there is a map. K algebra map. So consider this yi bar. So this it goes to some element in some regular function on x. So you call this equal to phi I. So these phi i's are regular functions on x, right? Now you define this x to y map phi or x to, so phi i's are regular functions. So that means on x, so that means it's a map from x to a1. So you define a map from x to an in this way that x goes to this is little x, or let's say p goes to phi 1 of p. So m, I think m, this is m, phi 1 of p, phi m of p. Now you need to show that x lands in y. Under phi, x lands in y. Right. So so that means if you take a polynomial g, suppose g is a polynomial, so that means g belongs to p. Ideal of y is p, right? Because p is a prime ideal. Ideal of y. So if g of, so such that if g of phi of p is 0, so you have to show that if I take any element in g in p, then g of phi p is g, because the p is the ideal of vanishing. So g of phi of p equal to 0. That is what you have to show for any point p in x. Then only it will x will land in y, right? For any g is any. But g of phi of p, this you check this. This is nothing but f of g bar of p. So this is, I will put a check here. G of phi of p is nothing but f of g bar of p. But f of g bar is 0 because after all it's a map from y to ox. So the p is oy is nothing but ax kx1 x2 xm by p. So p is going to 0. So this guy is 0. So this guy is 0. So that will say that this is 0. So g phi takes x to y, right? So this will say that phi takes, this implies phi x is y, and that is what you wanted, right? So this completes the proof. Okay. And as a consequence, you see that this for finitely generated K algebra, reduced K algebra, and affine varieties, this is these two categories. So this is sometimes it's called equivalence of categories. I will not say exact definition, but equivalence of categories is sometimes it's called that if you have two categories C and D, you say it is equivalent if there is a functor f which takes objects to objects and the home set. So in some sense that you have another function d to g, another functor from, so the g composition of f It's not exactly identity, but it is some kind of, it's a natural isomorphism is there with the identity functor. Similarly, A for G. I mean, I don't want to go into very detail, but yes, natural transformation. Natural transformation with the identity functor. Natural transformation. So between functors also you can define maps. Okay.
So in which case does bijective morphisms become isomorphisms?
Huh?
So when does bijection?
No. Bijective morphism did not be isomorphism in this case.
So what property of the category?
Equivalence mean?
Like in which case of the category does bijection imply isomorphism?
Set.
What is the thing which is missing which will prevent that? Like for non-algebraic
structure. So you have a structure, right? It's just not a set map. See, X is if we have a bijective map from X to Y, then there is some algebraic structure between X to X and Y. The algebraic structure is not preserved. So when you have a morphism, means it takes the algebraic structure of X to algebraic structure of Y, or right. So I'll come to that. I will give some example and I'll tell you that that is the case in the case of algebraic affine varieties.